start this recording here. All right, so let's see here. We'll do a quick review and then we'll get into some fun stuff, which kind of ties everything together that we've done so far. And I'm going to cheat a little bit this term, and I'll show you what I mean, but we're going to use Desmos quite a bit. So if you haven't downloaded the Desmos Graphing App, right? So that's the one that looks like, I don't know if you can see the little green app with the parabola and the sine curve or whatever. That's Desmos, right? So I'm going to be graphing in Desmos quite a bit, and then we've been using it to check our work for when we're finding those solutions. But I'm going to use it quite a bit today for linear programming. Now, linear programming, like I said, is something that I kind of go pretty hardcore with when we're in person, because then I get you to draw everything, and it's pretty fun. So, but now we're going to skip a little bit and we'll just do the kind of the take-home message. But first, we'll start with review. So, what did we do? We talked about functions, right? And how we can use functions. Functions take some input value and spit out some output value, right? So we talked about functions and kind of manipulating functions, where f of x is function notation, right? And so you read this as f of x, right? X is the input, where x is the input, and f of x is the output, which you can usually use interchangeably with y, right? If we're working on an xy plane. Okay. And so the profit of x, so the profit function, the profit of x is our most common function that we're going to be working with. The profit function is the profit function where x is the input, and we're kind of leaving it open. Usually it's the number of units that we're selling or producing or whatever. But x is we're going to leave that open. It's some unit, and the profit is the output. The profit is the output. Right? So if I sell, 4 things, then I make a profit of 4 times 2, maybe. Right? And then I have to take away my costs. Maybe I'm paying, $1 for each one produced, right? Something like that. And we'll build profit functions later. So that's why I'm kind of glossing over it here. But we need to know how to deal with profit functions. But for now, right, we're just saying, okay, we need some input, and then it's going to give us some output. And I'll give you the profit function for now. Okay. I think in the assignment, we're just using f of x notation, or just the regular function notation. So not quite dealing with the function or the profit function quite yet. And then we also talked about finding the equilibrium, right? So the equilibrium price and quantity. The equilibrium price and quantity for supply and demand curves. Supply and demand curves. Okay. That's the point of intersection, right? And so I'm not going to focus on, you know, if there's a fire one year, then what happens to the supply curve? No, I don't care about that. It does go through it a little bit in the textbook, but I'll leave that for another course with someone who's more able to kind of explain that to you. But just as a rule, right, our supply curve is always going to be positive, and our demand curve is always going to have a negative slope, right? So we talked about positive slopes and negative slopes. And so as a rule, right, and then we're replacing, for now, we're replacing, is it the quantity goes on the x-axis and the price goes on the y-axis. Okay, and then this here is the equilibrium. Okay, so we already spent some time solving systems of equations, and that's all we're doing here again, right? And that's what we're going to keep doing today in linear programming. So there. Anything else we did? No. Call that the end of our review here, right? That's from last day, but just to kind of refresh our memory, where were we? Okay. Section 2.3 is on linear programming. So section 2.3 is linear programming. Okay. Sounds weird, right? Sounds weird for us to be doing, but what we're going to be doing is just the basics of linear programming. Now, what that means is, so linear we know is a straight line, and the programming sounds terrible, right? It's not going to be that bad. So what happens is, if you are, so let's say you're running a factory, right? And you only have, there are usually restrictions that you're dealing with, right? You don't have unlimited labor, you don't have unlimited materials, and you definitely don't have unlimited time, right? And so, you know, in a day or whatever, so you're usually limited by how much you can produce. So sure, if you could produce unlimited amounts and sell unlimited amounts. Now, one thing that I do want to point out is for this course, we assume that you're able to sell everything you produce, right? And so, and that's a huge assumption. We know that, we understand that. But when I say, okay, you produce this many, we can also assume that you're going to be able to sell that many, which is definitely not the case, right? You might have some overstock, and but that's a different kind of economics course, right? And so for our purposes, we assume that everything you produce, you're going to be able to sell, okay? And immediately as well. So that's kind of weird, right? But for now, so we need some way to be able to deal with those restrictions, right? Those restrictions on materials and time and labor. So I like the idea of us running a factory, right? And so that's how I think it's the easiest way to think about it. So if you are running a factory, okay, to produce some good, right? It doesn't matter what. To produce some item, okay, you're limited by how many things, or you're limited the number of items. So if you're running a factory to produce some item, the number of items you produce will be limited by multiple factors. Will be limited by multiple factors. Right? Such as man hours, right? So just kind of how much labor do you have, right? So man hours, materials. What was the other thing that I was saying? Right, labor, materials. Those are our go-tos. But even things like maybe space, instead of something vague like space, maybe machines, machinery, etc. Right? Space is kind of a vague idea, so I don't want to have that one. Machinery, that makes more sense. Maybe I only have 4 machines, right? So maybe I have unlimited materials, I have unlimited man hours, but then I only have 4 machines. There's only so much I can produce, right? And so, so we're usually limited by multiple factors. Okay, so what we do is we want to optimize, and so an optimization is kind of it's a fun field in math, but we want to optimize how much we produce, right? So given some restrictions, we want to optimize how much we produce. So given certain restrictions, we want to optimize how much we produce. Sounds great, right? Okay, so that's awesome. How do we do that? Okay, so these restrictions usually come in the form of inequalities. Now, inequalities are things like less than, greater than, not equal to, right? And so our restrictions, or the restrictions, are usually given in the form of inequalities, right? So we need to do a quick refresher on inequalities before we can do anything. Okay, so first thing, right? Less than or equal to looks like this: less than or equal to, greater than or equal to, and you might remember, okay, the alligator eats the big one. That never really made sense to me. For some reason, I just can't. So the alligator's on this side, and anyways, now that I am familiar, like I know inequalities inside and out, now I get it. But I just remember having such a hard time wrapping my head around, okay, the alligator eats the bigger one. And so it wasn't until a student actually showed me that, okay, if you just make a little, and you know, the loser sign with your left hand, right, make an L, and then hold it down, and then you can match it to this less than sign, then you can just read across, right? So A is less than or equal to B, right? And so, and then if it doesn't make an L, then it's greater than, right? And so same thing here. If you don't have the underline, it's not equal to that value, right? So then it's just less than, greater than. and not equal to. Right, just as a refresher. Okay. The only restrictions on inequalities versus equal signs, okay, are if you're multiplying or dividing by a negative number. Okay, so what I want you to remember is you can treat all these as equal signs in your math. Okay, I'll just label these as inequalities. Okay. We can treat all inequalities as if they're equal signs in our math, unless we're multiplying or dividing by negative. Then we have to switch the direction of the sign. So I'm going to make a note of that here. We can treat all inequalities as equal signs in our calculations, except when we multiply or divide by negative. When we multiply or divide by a negative number, we must switch the direction of the inequality. We must switch the direction of the inequality. Okay. Okay. So, all right. Now, what's nice is we're not going to need to manipulate these inequalities a bunch, especially with the shortcut that I'm about to show you. But I do want to highlight kind of dealing with inequalities and just kind of making sure that they're not that bad, right? As long as you remember this one thing, okay, as long as I'm not multiplying or dividing by a negative, I can just treat them as equal signs, right? So they're not scary. But you do have to remember what they all mean, right? Less than or greater than, okay? So, so what happens is for these problems, and I'm gonna keep it nice and simple, so we're always gonna have the same kind of types of problems here. And so what's gonna happen is I'm gonna give you the set of restrictions. And then what's really, really cool about linear programming is if you need to optimize those restrictions, right? So really make the best use of all your resources, which I've given you in the restrictions. The optimized solution is going to be at one of the points of intersection, okay? And so I'll show you what I mean, and hopefully it'll make more sense as we go along. But let me write that down. So, so given a set of restrictions, the optimized solution will be at one of the points of intersection of the shared area. So we'll be at one of the points of intersection one of the points of intersection of the shared area. Okay. So how these problems are going to go is I'm going to give you a profit function, And the profit function, of course, we want to maximize, right? So we want to maximize this profit function. And just to give you like an idea, optimizing can mean to minimize or to maximize, right? Depending on, so if you want to minimize cost or you want to maximize profit, it just depends on what you're talking about. So for us, right, we're going to be dealing with maximizing profit given a set of restrictions. So for our problems, we will want to, and so I'm only going to do one type of problem for this whole section. So just like solving systems of equations, once you have the mechanism in place, then you just need to kind of remember the flow of how to solve these, and then you'll be able to solve all of them, right? And so, and I'm really just adding a few extra steps to solving systems of equations. So, so for our problems, we will want to maximize a given profit function, which we're going to denote just by a capital P, which is confusing because earlier in the supply and demand economics, we used capital P for the price, but it depends on the context, right? So sometimes we have to be a little bit flexible. So for our problems, we'll want to maximize a given profit function, which we'll denote by P. Okay, I'm just going to say subject to, I didn't want to, but subject to a list of restrictions. Okay, so what we do is we're going to draw those restrictions on the same graph. Okay, so what we're going to do here, the steps that we're going to follow are draw the restrictions all on the same graph. Draw all restrictions on the same graph. Okay. The second thing we're going to do is we're going to find the area where all those restrictions overlap. Okay. So find the area where all restrictions are satisfied. Okay. So we're going to find the area where all the restrictions are satisfied. Okay. So I'll go through the list of things that we're going to do first, and then we'll do an example, and then hopefully it's going to be one of those things where we'll have to do a couple of examples before it's going to make sense, right? So just kind of hang tight, trust that it's going to come together. So we have to find the area where all the restrictions are satisfied, and then find all the points of intersection. So identify all points of intersection of the area from step 2. Of the area from step 2. Okay, so you're going to find that area, and it might look something like, just to give you an idea of usually what's happening is x has to be greater than 0 and y has to be greater than 0. And then we might have a line like this, and maybe we'll have a line like this. Okay. The shared area would be something like this, okay? So the inequality would say, okay, it has to be less than this line and less than this line, okay? And so we would draw those lines, and I showed you how to draw those lines by hand last day, or maybe it was the day before, I can't remember. We need at least 2 points on the line, and then we can draw them. And then we're solving systems of equations here to find the points of intersection. So here we'd have a point of intersection, here we'd have a point of intersection, here we'd have a point of intersection, and there we'd have a point of intersection. So here, find the area where all restrictions are satisfied is going to end up looking something like this, okay? And usually what happens is and always in our case, we start here at 0, 0, and we just kind of bloom out until we hit a wall, right? And then that's the area where all the restrictions are satisfied. Then we go through and we identify all the points of intersection, right? So here we'd have 1, 2, 3, 4 areas of intersection that we would be interested in. Now, what happens is the profit function is maximized at one of these 4 points, right? So you can have X, Y coordinates anywhere in here, but it's maximized at one of these 4 corners, okay? And so find the ordered pairs, right, which are X comma Y, of all points of intersection from step 3, okay? And then your 5th step is the profit function. So that's the first time that the profit function comes into play. The profit function will be maximized at one of those XY coordinates, okay? Substitute each of the XY coordinates, or each of the XY ordered pairs, let's say that instead, into the profit function, which we're calling capital P. So you're going to substitute each of those pairs into the profit function to identify which ordered pair gives you the largest profit function. To find which XY ordered pair yields the largest P. Okay. So imagine X is maybe how much material you have, and Y is maybe how many machines you have, right? Then we would be restricted to how much material do I have, how much machinery do I have, and that's going to limit my profit function. Okay, and so now let's do a problem where we're actually going to work through this thing, because here I know that me walking through these steps does not make sense. So it would be weird if you did not feel confused right now. Okay, so if you're feeling like, hey, that makes sense, that is great, very impressive, but I don't expect this to make sense quite yet. But it is going to be really good to have this this list of steps to be able to refer back to later on. So what all of these problems are going to look like are like this. And I'll show you how we're going to do a kind of a shortened version because I'm not getting you to draw things by hand. Usually you'd have to draw it by hand. Okay? So, example. if I get you to, so this is how all these problems are gonna go, okay? And if you have the textbook, right, then all the suggested exercises for this section all look the same. So there's really only one problem, but what's nice about it is it incorporates everything that we've learned so far, right? So on my end, it's a really nice way to be able to test, okay, do you know how to draw a line? Do you know how to find points of intersection? Do you know how to work with these ordered pairs, right? So if you think about it that way, how good it is for showing off all your knowledge, maybe that'll help. So we want to maximize, and then I give you the P is equal to X plus 1.2Y, subject to, and then I give you the list of restrictions. 2x plus y has to be less than or equal to 180. Okay. X plus 3y has to be less than or equal to 300. And then x greater than or equal to 0 and y greater than or equal to 0. Those are always going to be conditions, and we'll just jot them down here. But they're kind of ignorable, right? Because all this is saying here is that on our graph, this is our x-axis and this is our y-axis. All this is saying is that my x's have to be greater than or equal to, sorry, that's my y's has to be greater than or equal to 0. But also my x's have to be greater than or equal to 0. Right? And so this is just restricting me to my positive x's and positive y's, so that one quadrant, right? Remember, we do have 4 quadrants, 1, 2, 3, 4, but now we're saying, okay, we're going to restrict ourselves to having positive values for x and y. It doesn't make sense to have negative materials, right? It doesn't make sense to have negative number of machines. So that's why we have those. So that's all these things are saying, is that, okay, we're restricted to this, this one quadrant, okay? So the conditions that we're going to be working with are these two. 2x plus y has to be less than or equal to 180, and x plus 3y has to be less than or equal to 300. What I want to do, just to show you, I want to do these by hand, but then I'll show you how to do it in Desmos, and then you can just do it in Desmos from here on out, right? But I want to show you how to do it by hand because it's going to be useful. So we need to work with these restrictions. Okay. So what we have to do is, all right, first thing I'm going to do is I'm going to map these 2 restrictions. So I'm going to draw these. They're just straight lines, right? I can rearrange them to be kind of ignoring the inequality for a little bit, right? I can rearrange these to be a straight line, right? So I'm going to call this, very familiar, right? I'll call this equation 1. And I'll call this equation 2. That should feel familiar from solving systems of equations, right? So it's just an extension of that. Okay, so equation 1, I can rewrite as 2x plus y is less than or equal to 180, right? If I solve for y here, I have to subtract 2x from both sides, right? But I can do that. Remember, I only switch the sign if I'm multiplying or dividing by a negative, which does not apply here. So 180 minus 2x. So what we're saying is that y has to be less than or equal to 180 minus 2x, okay? So what that's going to look like if we just draw it is gonna look like this. So you can find the X and Y intercepts, but I'm gonna show you how to do it kind of by hand, and then we'll do the shortcut versions. But definitely, if the points that you want to use to draw this thing are the X and Y intercepts, that's great, that works. Okay, so just as kind of a heads up, I've got a negative slope here, so I already know that this thing is going to go down like this, right? So in general, I'm going to have this downward slope. Okay, so what I'm going to do is I'm going to draw y equals 180 minus 2x. And then I just have to remember that, okay, the area that I'm interested in is everything below that line. Okay, so here we draw the line y equals 180 minus 2x. And then the inequality says the region that we're interested in is everything below. The inequality says the region of interest is everything below the line. Okay, so what that's going to look like, right, without kind of figuring out how to draw the line quite yet. Okay, this is my line 1. Okay, so everything that I'm interested in is everything below this line, so everything kind of on this side of the line. This would be considered above the line. So that's the area that I'm interested in. Now, you can go ahead and draw this line, right? But what I want to do is I'm just going to draw this in Desmos. Okay, so let's see here. I can't remember if it deals with, let's try the inequality, because we do have the inequalities here. Y is less than or equal to 180 minus 2x. Oh, it's going to be quite a large area, but that's where, if you zoom out enough, right? That's my first restriction mapped out, right? Which is what we saw when we talked about it. So instead of drawing this thing, this is where I'm cheating, and I'm just going to let you use Desmos instead, right? So we can use Desmos to find the points of intersection, for example, right? Okay, so these are all whole numbers. If we had decimal values, we would need to find the exact answer, but that's okay. All right, so instead of drawing these by hand, we're going to use Desmos. And I'm going to map these coordinates onto the graph that we sketched out. So, or maybe not, because it's too small. Instead of drawing the line by hand, we will use Desmos, right, to draw the restrictions. To draw the restrictions. Okay. So the first one we already mapped, right? And then my second restriction, I'm going to do the same thing. I'm going to solve it for y equals and have it in the format of y is less than or equal to mx plus b. And that'll just be easier to work with, right? So equation 2, x plus 3y oops, x plus 3y is less than or equal to 300, right? Yeah. Solving for y here, a little bit more work, but that's okay. We get 3y is less than or equal to 300 minus x, and then divide it by 3. So y is less than or equal to 300 minus x divided by 3. I'm just going to leave it like that. I can plug that into Desmos, okay, and make sure you draw it on the same graph. So here I'm going to do another line, and I'm going to have y is less than or equal to, and then in brackets, to make sure that everything's going to be divided by 3, I'm going to have bracket 300 minus x, I want to say, yeah, end bracket divided by 3, right? Make sure that it looks the same as what you found. Okay. All right, good. And then remember, the x is greater than 0, y is greater than 0. You can map that out here. X has to be greater than or equal to 0, okay? And y has to be greater than or equal to 0. But then it just makes it really dark to see, right? So I'm just going to remember that I'm working in the first quadrant, and I'm actually going to remove these restrictions because it makes it hard to see the overlapping area. Whereas here, if I'm trying to find, oh, it won't let me do all of them at the same time, but if I'm trying to find the area of the overlap, right, then I'm restricted to going between here, 0, 100, 48, 84. Hey, that's confusing. And then this x-intercept 90, 0. Okay. So what I'm going to do is I'm going to map this out in our notes. So in Desmos, we find the area of overlap of all the restrictions is this. So here, I'm just going to draw it out, sketch it out rather. Whoops. So I've got my x, y here. Okay. And what did it look like? Okay. I've got a line like this. Okay. Got a line like this, maybe. And a line going further out. Like that, maybe. Okay. So the overlap is going to be this region here of all my overlaps, right? So x has to be greater than 0, so that's what puts me on this side. And then y has to be greater than 0. Oh, are you finding that you're doing one where it doesn't look like this? Because they'll all kind of look like this.
Yeah, mine doesn't look like that. Do you need to have them set up in like a special graph or something?
Yeah, so let's go back to what mine look like here. Do you have them set up like this? So I solved for y first, and then just had y as less than, and that might make a difference. Maybe.
Yeah, they look the same as the calculations, but they're not showing up the same as in the graphs.
Weird. Is it just all colored in? Because then you might have to zoom out a little bit. That's the only thing I can kind of think of.
I didn't, on one of them, I didn't change it to do y is, I didn't do it so that the y was isolated, and I got the same answer. It shouldn't really change it because it's the same equation, right?
Yeah, totally. Uh, hmm. Okay, so yeah, so it should, yeah, so you don't have to manipulate it. I just find it's easier to see that it's a straight line if I manipulate it a little bit, but you don't actually have to. But yeah, make sure that what you're plugging in, maybe if your graph doesn't look like this in Desmos, try just plugging in those raw conditions, right? So what was it? 2x plus y has to be less than or equal to 180. So do something like 2x plus y has to be less than or equal to 180. 80, right? And that should give you the same line. So try that just to make sure that Desmos is behaving. Let me
Okay, I
know if
restarted on a new graph and it's looks like it's starting to look better this time.
good. Awesome.
Thanks.
Yeah, so yeah, make it behave. Good. Let me know if it doesn't work. So I'm going to copy these intersections because remember, these intersections are where we optimize our solution. And in this case, optimizing means maximizing. Oh yeah, to divide the 300 minus x, you have to make sure that you put 300 minus x in brackets. And then, so let me just type that out again. So here, bracket 300 minus x, just to make sure it's all divided by, and then end that bracket and then divide it by 3. Yeah. Because otherwise it might just do x over 3 instead of 300 minus x over 3. Awesome. Cool. So what we're going to grab from this are the intersections of that shared area, right? And so first one I'm going to grab is at 0, 100. Okay. The second one I'm going to grab is at 48, 84. So I'm going to copy those out here. So this is at 0, 100. This is at 48, 84. Notice that, okay, so this is the y-intercept for the second line, right? So you might have to solve for that. We're going to use Desmos, so I wouldn't worry about it too much. But here, this is just solving the system of equations to find that point of intersection, right? Which we've practiced quite a bit now, right? And so here, this is just finding that point of intersection if you had to. And then what was this one? I want to say 90, 90 and 0. And then one thing that I don't want you to forget about is that 0, 0 is also a point of intersection. It's never going to be an optimized solution, but it is kind of an extreme of your solution, right? Use 0 material and use 0 machines, you get 0 profit, but it is a solution. And it's an extreme solution. Okay, so the 0, 0 was always going to be an option. And then we kind of bounce out from 0, 0. We go until we hit a wall. And then that's going to be our region. Okay. What this is telling us is that, okay, given our restrictions, anywhere in this region, so any XY point in this region is going to be a solution that we could do, okay? But what we said was, okay, our optimized solution, our optimized coordinates for X and Y are going to be at one of these 4 points of intersection. And sometimes we could have 5 points of intersection, right? Something like that. So it can get a little bit crazy, but if we're using Desmos, it's not so bad, right? Imagine how terrible my other students have had it. They've had to draw these lines, find the points of intersection, then use it. We just get to jump straight to the fun part. So now we have these points of intersection from Desmos, right? And so now this is where we bring back the profit function. So what I want you to, I'm gonna try to slow my scroll here because it's been lagging. It was lagging yesterday and lagging today, I don't know. Even though, oh, I went slow, but not slow enough. Even though this profit function was introduced as the first thing, we haven't touched it yet, right? And so we don't actually touch the profit function until the very end, okay? So that's what, because I know when you're trying to solve these problems, people usually want to work with this equation first, but we just kind of parking lot it until the very end when we're trying to maximize this thing. What we've found is we've mapped all these restrictions, and now, right, we've got XY ordered pairs that we can plug into this XY here, and we're able to maximize, which we're told to do, the profit function, okay? So P is X plus 1.2Y. P will be maximized at one of these points of intersection. Okay, so what I like to do is I like to organize it as a table because that way I can kind of list things. And so here, I'll list my intersection, which is in the form of X comma Y, right? It's an ordered pair. And so I'm gonna list my intersections. I usually start at 0, 0. And just in case I have to mark your work, then maybe it's a good idea to just start at 0, 0, and then just move away, go clockwise, right? So it doesn't actually matter, but makes it easier to read. So 0, 0 is an option. It's not a good one, but it's an option. It's extreme, all right. Okay, so we've got 0, 0. 100, sorry, 0, 100. Put it on the wrong axis. 48, 84, and then 90, 0, so I don't have to scroll back up again. So 48, 84, and then 90, 0. So I list my intersections, okay? And then I'm gonna divvy this up. And up here, I've got P equals X plus 1.2Y. So what I'm gonna do is I'm gonna plug in X equals 0 and Y equals 0, and that's my profit at 0, 0. It's gonna be 0, no surprise there if I'm using no materials and no machinery, if that's what X and Y are, which seems likely, right? Then my profit is gonna be 0, okay? So here, my profit is gonna be 0 plus 1.2 times 0, which is gonna be 0. Probably not a maximized profit, okay? So then I do the same thing with my other XY coordinates. And so I've got P is 0 plus 1.2 times 100. Should be 120. P is 48 plus 1.2 times 84. I'm gonna just use my calculator on the side here. So 84 times 1.2 plus 48. Because I'm dealing with money, I don't need to worry about the fractions. I can just go straight to decimals. And so 148.80. And I'll throw dollar signs on there. Why not? You don't have to, but just to kind of justify using the decimal. Okay. So far, that's my maximized profit, right? That's the largest one of these three. That's the one I want. Okay, but let's just do the last one just to make sure. P is 90 plus 1.2 times 0, which is going to be $90. Okay. All right. So what we found is that this guy here, that's our maximized profit. We find the maximized profit is, and I'll just say P is equal to 148.80. And when does that happen? Well, it happens when X is 48 and Y is 84. Regardless of what, for us, it doesn't matter what X and Y are, right? And so we just need to know, okay, how do we read this thing? When X is 48 and when Y is 84. When X is 48 and Y is 84. So pretty fun problems, right? Especially when you get to tie it all together. And it just hinges on, okay, the points of intersection of that shared restriction, shared area of restrictions, yeah, will yield the maximized profit, right? And in this case, it happened at 48.84. Great, and we get a profit of 148.80. So many 48s, 8. Okay. Let's do another one. I'll steal it. Steal it from the textbook here. I always do. Any questions before we do another example? I think another example might do us some good. Okay. So for us, right, because I'm not getting you to draw these lines or even calculate the points of intersection, right? For us, we just need to be able to get these points of intersection and plug them in here, right? So I'm eliminating quite a bit of work for you. But this is all work that you can do by hand because I've already shown you how to do it, but it's quite a bit of work. All right. So let's see here. What if I want to maximize, because I haven't seen any questions come up, but if you do have any questions, let me know. P is 2x plus 5y, and I want to maximize it subject to (2x plus y is less than or equal to 16. 2x plus 3y is less than or equal to 24. I'm going to add another restriction here. Y has to be less than or equal to 6. Okay. And then our go-tos, x is greater than or equal to 0 and y is greater than or equal to 0. Remember, these two, I'm just going to ignore when I map this out because it's going to get too crowded, right? But I just am sticking to the positive quadrant. Okay, so for us, how we're going to solve these, right, is we're just going to go straight to Desmos to find that area of overlap. And how about we just whittle it down so we don't have to do hardly any work at all, only the fun parts. How about we do what we did earlier where we just plug this in? So just as it appears, let's just plug it into Desmos and see what the area of overlap is. Let's do it. Okay, luckily I've got it here on the side, so just reminding myself that I don't need to flip back and forth. Okay, so it was 2x plus y has to be less than or equal to 16. Okay. So it should make you a line. On to the next one. 2x plus 3y should be less than or equal to 24. Okay, I'm going to zoom in on that, but I'll do the last one first. And then y has to be less than or equal to 6. Okay. So if I zoom in on this area here, okay, quite dark, but notice that we're going to have 1, 2, 3, 4, 5 intersections now, right? So you start at 0, 0 down here. Oh, I can't show you. But you start at the origin, 0, 0, and then you bloom out until you hit your first line, and then that's where you stop, and then we're restricted by all those lines. So I'm gonna try to copy this into our notes. Okay, so from Desmos, we find that it looks something like this. I'll draw my y equals 6 line first. Great. And then I had 2 lines. One sloped. And one came from kind of up here, maybe. Something like that. Okay. Notice I'm not drawing any grids or anything. What a mess I would make. Okay. But the area of overlap here is going to be from 0, 0. I go out until I hit till I hit my first line. Okay. So then I'm restricted to this area here. Ah, got carried away. Maybe I'll use a more subtle, the highlighter. That's my area. Okay. Of overlap for all of these points. Okay. Just grabbing the values from Desmos. Let's just, well, we know this area, this intersection is at 0, 0. This intersection, I know because this line here is at y equals 6. And so this should be at 0, 6. So now, don't forget about this little guy, right? I need to find the values for these 3 points, okay? Which you can do by hand, right? By finding the points of intersection of this line and this line, right? Of this line and this line, and obviously you'd have to label them and everything, but and then find the x-intercept of this line. Okay, but we're skipping straight to the good stuff. I get carried away sometimes. 3, 6, and 6, 4, and 8, 0. Let me just quickly get that down. 3, 6, 8, 4, and 6. Hey, 3, 6, 6, 4, and 8, 0. I messed that up. There. Now I have all these intersections, right? So what I want to do is I want to translate those intersections into profits, and then I'll be able to find the maximized profit. Okay, and so my intersections, I'll start at 0, 0, and then go clockwise 0, 6, just for some kind of rhyme or reason in how I list them. 3, 6, 6, 4, and 8, 0. It is not until now that we introduce the profit function. Right now, we use this to optimize our profit function, which was 2x plus 5y. So same idea here. Now I go through and I plug in my xy coordinates into this x and this y here, and I find the largest p. So p is 2 times 0 plus 5 times 0. That's a profit of $0. No surprise, right? And I will take off marks if you don't tell me. So if I am looking at your work, then if you don't tell me that 0, 0 is an option, because it's always an option for optimizing, right? But it minimizes your profit function, and that's not what we want to do, right? But it is always an intersection that you have to consider. P is 2 times 0 plus 5 times 6. 5 times 6 is 30. Now I'll probably need to bust out my calculator. 2 times 3 plus 5 times 6. Well, maybe not yet. 36. So far, that's my largest profit, right? But I've got other options. So 2 times 6 plus 5 times 4. 12 plus 20. Let me just confirm that. I don't want to screw things up here. 32, good. And then 2 times 8 plus 5 times 0. It's going to be 16. Okay. Here, right, what we found is that our maximum value here out of all of these, for example, if I asked you, hey, which one of these do you want? You would probably say 36, right? That's the largest one. So then the follow-up question would be, okay, well, what should my X and Y be, right? X maybe is the how much material should I buy and how many machines should I buy? You should buy 3 units of material and 6 machines, right? And so that's how we're answering those business questions, right? And so 36, that's my highest profit. That's the one I want. So I write a little concluding statement, of course. The maximized profit, the maximized P is equal to 36 at X equals 3 and, hey, weird, and Y equals 6. That is coinkydink. 36, 3 and 6, pure coincidence. Okay. So that's how we're going to do. So that's how we will do linear programming this term, kind of taking some shortcuts using Desmos. But the important thing is being able to map those restrictions, find those intersections in Desmos, and then using them to maximize your profit function. Good. Let's do a little bit of a break. Just, sorry guys, a 3-minute break. I'll try to end a little bit early, how about? And then we'll start chapter 3. We'll start 3.2. So let's do a break until, oops, I want to combine my until 11:15. 2-minute break. It's enough to grab some water. Pick back up here, because I don't want to spend too much time in break mode. I lose it all. So like I said, we're going to start chapter 3. Chapter 3 in general is called what? Business economics, not very telling, but chapter 3, business economics. The good news is, if you didn't like what we were doing earlier in chapters 1 and 2, well, 1 is just kind of math stuff. But if you don't like solving systems of equations, don't worry, you won't have to do it anymore. It will come up on the tests and stuff, but now we're kind of moving into fresh material.
Professor,
Yes?
for the questions that we have done earlier, so to find the values of x and y, are we going to use the Desmos app
Yes.
for everything?
Yeah.
Okay.
So I don't need you to solve it by hand. You can,
Okay.
just for practice,
Okay.
but you don't have to. You
Okay.
can just use them.
So all
Yeah.
the values we can find like this only, or just for the greater and smaller ones?
No, you can do it for all of them.
Okay. Thank you.
Yeah, so you'll be allowed to use Desmos. All your tests are open book. So, I mean, as long as you're not working with each other and what you're doing is kind of your own thoughts, I encourage you to use Desmos to check your work and to do problems like that we were just doing. So definitely you're allowed to use Desmos for the tests and the final exam. Okay, so that'll be good. Okay. All right, so we're gonna leave 3.1 until section 3.4. It'll just make a little bit more sense doing 3.1 and 3.4 together. And so we're gonna skip straight into 3.2, which is called merchandising, which is also kind of cryptic in a way. But what we're gonna do is, we're just gonna break it down here. So merchandising is, now we're gonna get into just kind of some business math, right? So what we were doing before was just kind of solving systems of equations and really just pure math stuff. Now it's going to require, we're going to have more word problems. It's going to require kind of knowing some terminology. And so imagine you're running a store, right? We understand that when I go to a store, so if I go to a corner store, for example, and I buy gum for $2, I know that the store didn't buy it for $2, right? The store bought it for maybe $1.50. I don't know. That means that they're making 50 cents off of my purchase, right? And that's how all these things work. We understand that that's how it is, right? And so what we need to develop is we need to develop the math behind showing that relationship, right? And so a store buys a product for a net price, which we denote by N. Okay, so we need to establish some terminology and some shorthand that we'll be able to use in our calculations. Okay, so a store owner purchases a product for a net price, which we'll denote by capital N, okay? And sells it often at a list price, which is the suggested retail price. And sometimes they'll put stuff on sale and then that's gonna be the sale price. But for now, let's just think about the list price is the price that we pay. So a store owner purchases a product for a net price and sells it for a list price, which we'll denote by L. And L is the suggested retail price. We've all probably shopped at Winners, for example, on their price tags, right? They always have their suggested retail price and then their special price. And so in that case, the list price would be the suggested retail price, and then they would have a sale price. But for now, let's just assume that the two are the same, right? Nothing's been marked down. So, so you're a store owner, right? And you purchase something for a net price and then you sell it for a list price, okay? And the net price is the list price less some discounts. The net price is the list price, and maybe I should capitalize it just to emphasize, is the list price less a trade discount, oops, can't write anymore, less a trade discount, which we'll denote by a lowercase d, right? Or potentially multiple trade discounts, okay? There could be multiple companies in the supply chain, right? And so you might buy it from a distributor and the distributor buys it from the manufacturer, right? And at each level, there's some sort of trade discount. So less a trade discount or multiple trade discounts which we denote by D1, D2, up to D, and then I want to use K, but I just want to make sure. I'm going to use K for now. Oops. Usually I do a little script K here, but it's not showing up. Okay. So allowing for K discounts. Allowing for, oops, K discounts. What I want to do is I just want to double check. So this is the first time that we're dipping into our formula sheet. And so I want to pull up our formula sheet here. It's probably going to make me log in again. Oops. Come on. And our formula sheet is just posted at the top on our Moodle page. So if you haven't grabbed it already, you might want to download it and have it, or even print it off, compromised password. Yikes. Okay. That's bad news. Because I can't remember any other passwords. Okay, so I'm going to bring this formula sheet into our notes here, create a new note, add to 14. Okay. So what we're going to do is we're slowly going to pick away at all of these formulas, right, until we've covered them all. Okay, so if I go here, right, from our formula sheet, we're in the merchandising section. Yeah. And using K, it does match what I was doing here. Okay, so mathematically, if the net price is the list price less a trade discount, then how we denote that is, okay, the net price is the list price times 1 minus D, right? And so the D is the amount of the discount. The discount is typically a percentage, but remember the percentages we have to turn into decimals, okay? And so we show these relationships mathematically. Oops. Mathematically by the net price, right, is the list price times 1 minus D. And I'm going to make some notes here. D is the trade discount as a decimal, right? So it's usually given as a percentage, but for all these calculations, right, we're going to convert it to a decimal. So this is the trade discount as a decimal. Okay, so for example, a 7% trade discount, you would have to use 0.07, right, divided by 100. Or you can use that fancy, well, not that fancy, percentage button on your calculator. Doesn't matter. Okay, so that's your D. That's the hardest one to deal with here. The list price is the suggested retail price. Okay. And the N is the net price, which is the price the store owner pays. Okay. That's if you have one trade discount. If you have multiple trade discounts, right? So here, that's the first one where we started. So the net price is the list price times 1 minus D. If you're given multiple trade discounts, you just tack them on in order, right? So times 1 minus D1 times 1 minus D2, and then multiply through until you've covered all your DK discounts. So we do that a lot. We use subscripts to kind of denote multiple discounts. Okay. So here, just to make a little note, this is if there's one discount, and this is if there are multiple discounts, multiple trade discounts. Trade discounts are going to be different from, because remember, the list price is the price that I pay as a consumer, right? And so when we're talking about sale price or kind of sale prices to us as the consumer, that's what we're going to deal with down here. Okay, so so just hold off on that. For right now, we're just talking about, okay, if you own the store, on the store owner side. Okay, so let's do some examples here and see what we can do. Start nice and slow here. If Toshiba sells a laptop, Toshiba sells laptop computers. Just going to copy this out. From here on out, I forgot to do it for today, but from here on out, I'll probably have a printout of all the examples that we're going to do, which I'll post before class. And so that way we don't have to write out all the examples and you can just kind of refer to them as we go. So I'll have that prepared, but for today I forgot to do that, so that's okay. Toshiba sells laptop computers to retailers for $2,195 after a trade discount of 35%. What is the list price of the laptop? What is the list price of the laptop? Question mark. Okay. Now, for me, a lot of these problems, how they're worded, can be a little bit vague, right? So they sell this laptop computer to retailers for this amount after a trade discount. So does that include the trade discount or no? If you're finding that it's kind of tricky, then once you read this part, right, what is the list price, then we can assume that this is the net price, right? And then after a trade discount. So sometimes we have to make kind of these extensions and that's okay, right? But we've got one trade discount, right? So you kind of hinge it on, okay, what's it asking for? Okay, well then this must be the net price, right? I tried to pick problems where it's obvious what each thing is, but not always easy to do. So we've got one trade discount that we're given of 35%. So I'm going to use the one trade discount formula, which probably looks familiar, right? From the quiz, you had to solve for one of those variables, okay? And maybe after this example, how about we go through and we solve for each of the variables? So let's, well, we've already solved for N, but we can solve for L and we can solve for D. So I'll show you how to do that. And that's just good practice. So for each of these formulas here, in fact, all the formulas as we work through them, it's really good practice to just rearrange each of them and solve for each of the variables individually, right? It's pretty common that I ask you to do that. So let's do that as some practice in a little bit here. Okay, I'll let it catch up. So my net price is $21.95. Mostly from context, right? So if it's not obvious, then it is just from context. So that can be tricky in the beginning. The list price is what I want to solve for. And then 1 minus D, but remember 35%, I have to make it a decimal, so 0.35. Okay. So what I'm going to do first is I'm going to simplify 1 minus 0.35, right? 1 minus 0.35 is 0.65, but let me confirm here. It is. So then I have 2195 is L times 0.65. To solve for L, I have to divide both sides by 0.65, right? And then I always do that revolving door where I put L on the left-hand side. So I'm gonna do this in one kind of quick motion. And so I'm gonna put L over here, 2195 divided by 0.65, right? So I'm doing two things in one swoop, right? I'm shifting my revolving door. If A is equal to B, then B must be equal to A, right? And so I can do that, which is pretty common that I'll make this shift here. I'll move whatever I'm solving for to the left-hand side, but then I would also divide the 0.65 over, so that moves over here, okay? All right, 2195 divided by 0.65. The list price. Now what I want you to do is I want you to write out all your decimal places before you round, right? Just in case you're rounding incorrectly or just kind of copy things out wrong. So the list price without rounding is 3376.923077. The list price is money, so I'm allowed to round to 2 decimal places now. Right? So the list price must be $3,376.92. So let's see here. That's kind of the end of that example, right? And I guess I should write a little blurb. I'm not going to, but technically we should. But as long as we're able to get that number, then I'm happy. Going back to one of our quiz questions, right? So from n equals L times 1 minus D, solve for L and solve for D. L's not bad, we just did it, right? So n is equal to L times 1 minus D. If I have to solve for L, I'm trying to get L on its own, right? So then I have to divide both sides by 1 minus D. So then I get n is 1 over 1 minus D is equal to L. Or if I switcheroo them like I did earlier, I can write it out the other way. L is n over 1 minus D. If I have to solve for D, that's a little bit more work, right? And I think that's the one.
Emily, can you just put the other example back up that you just erased?
Oh yeah, well I just had this on the left-hand side.
Okay.
And the L on the other side.
Okay, thank you.
And then I've got a page break here, otherwise I would do it. But I just had them switched. Okay. So, well, I guess I can move it up here. Let's do this. We can have it all. N divided by 1 minus D equals L. Or like that. That's what I had. So then I've solved for L. So now if I want to solve for D, I'll start at n equals L times 1 minus D again. And I'm trying to get D on its own. So what I need to do is I need to divide both sides by L to kind of shake out that 1 plus D. So what I get is I get n divided by L is 1 minus D. And from here, there are a few options that you have, right? What I'm going to do to eliminate this negative D or minus D is I'm going to add it to the left-hand side, okay? And that'll make it positive, but also move it to the left-hand side, which is typically where I want it. So it's kind of a 2 birds with 1 stone situation. N over L plus D equals 1. Getting D on its own, I have to subtract N over L from both sides, right? So then I get D is 1 minus N over L. Okay. I'm pretty sure it accepted this version, right? Or if you force the common denominator, right, then you would have to multiply this 1 by L over L. So this becomes D is L over L minus N over L. Oops. So D is L minus N over L. But the key is that you need to break out the 1 minus D on its own, and then you'll be able to isolate the D. Making sure you keep that 1 there. So how about we do another, so that's how we solve for these variables on their own. Now, if we have multiple trade discounts, we would need to know how many we have, and it just makes it a little bit harder, but it's still manageable, but it's not something that I want to do with you. So how about we do, how about we do one more example, and then I'll let you go. So let's see here. Let's do an example of multiple trade discounts, and then we'll do some, we'll start with some more examples next day. So Rona can purchase bags of soil from their distributor for a list price of $3.25 less discounts of 25% and 10%. What is the net price? Okay. So here, right, what you're going to start to find is when you read these problems, right, we've already had a look at your formula sheet. There are a lot of different variables. In this case, we've only introduced 3 variables, right, N, L, and D. But from the question, you'll be able to identify the formula that you should be using. And that can be tricky in the beginning, right? But here it's asking for the net price. We're given the list price, and it also mentions discounts. And so from there, I have a pretty good idea that I should be using N equals L times 1 minus D1 times 1 minus D2, right? Making room for 2 trade discounts. Okay. So here I want to find the net price, which is just find N. So I'm going to put in my list price in each of my discounts, and then I'll be able to just solve for N. So N is the list price of $3.25. And the discounts, it's really important that you have 1 minus the 0.25 and then times 1 minus 0.1. If you did just times 0.25, it doesn't work. So times 1 minus 0.25, and then times 1 minus 0.10. I always simplify inside the brackets before I go ahead and do my calculation, right? And so what this becomes is my n becomes 3.25 times 0.75 times 0.9. And now I can just multiply this out. I'm going to do it on the side here, so I'm not flipping between the screens. 3.25 times 0.75 times 0.9 puts me at, and I'll give the non-rounded value first, 2.19375. So n, because it's money, I can round it to 2 decimal places, properly rounding in this case 2.19. So $2.19. So what we're going to start doing next week is we're going to talk about equivalent discounts. So what would be one discount that would be equivalent to 25% and 10%? As a heads up, it's not 35%. Okay, so so that's what we're going to deal with, and that's what we're going to work with, and that's where we're headed. But I think that's good for today. As promised, I'll end a little bit early here because you didn't get any break. All right. Any questions before we go? Awesome. Then I will see you on Tuesday. Have a good weekend, guys.
Thank
I
you.
just have a question. So you don't do anything with the like exponents by the D's, like in the brackets, like the 2? You don't?
Oh, these are subscripts, right? So
Oh,
you want to
okay.
be, this is just saying discount 1 and discount 2.
Okay, sounds good.
Cool. Awesome.
Thank you.
Have a good weekend.